Hi, everyone. Let's continue talking about uncertainty. What we're going to talk about now is called propagation of uncertainty. We're going to find that if we know the uncertainty in position at one time, then as time goes on, the uncertainty in position will typically grow. Okay? This is something that's not talked about in detail in our textbook, but I think it's important. Here, let's take a look. Here's the idea. Let's suppose at t equals 0, that the uncertainty in the position of our particle is the minimum uncertainty that it can be. Let's call it delta x0, where delta x0 times delta p is equal to h bar over 2. Okay? That's the smallest it can possibly be. Then, over time, delta x will grow. And that's because there's another source of position uncertainty. Since delta p is not equal to 0, and since delta p can be written as m times delta v, the uncertainty in velocity, where here I've used a non-relativistic formula, of course, there's another source of position uncertainty. Let's call it delta x sub v, which is just delta v times time. Okay? If I don't know how fast the particle is moving, then after some time, I, of course, won't know where it is because it may have moved some distance due to its velocity. Okay? So this is because of this, the position uncertainty grows. Of course, using the uncertainty relationship, we can rewrite that term as h bar over 2 m delta x times t. Okay? But very good. Now when t becomes large, delta xv will typically be much greater than delta x0. It'll completely dominate the uncertainty. And so in that case, when we calculate the uncertainty in position, we should use this result, okay? Excuse me. In general, we can combine the two kinds of uncertainty. And I'll write down a formula, but it's not one that we'll use very much. In general, these are two separate, independent uncertainties, and so they add the way that uncertainties add in the laboratory. That is, we have to square them and add them, and then take the square root. Like so. Okay. Let's use these results to do an example. Okay? Okay, here's the example. We're going to see if we can drop electrons into a cup. So we're going to drop the electrons. When we drop them, they're going to pass through a narrow slit, 1 millimeter wide. Well, not that narrow. And they're going to fall straight down, and we'd like to see if they'll land in a cup that's 1 centimeter wide, that's 5 meters below us. So if we're very, very careful, can we get all the electrons to go into the box? That's our question, okay? And you'll see that the uncertainty principle has something to do with the answer. Let's take a look. So when the electrons start their trip, they start with an uncertainty in their position, lateral position, of 1 millimeter. okay? And because of that, we know that they have an uncertainty in their velocity, which will be h bar over 2m delta x 0, okay? And putting in numbers here, we have h bar is about 10 to the minus 34. I'm going to leave off the units if you don't mind. Divided by 2, mass of the electron about 10 to the minus 30. Delta x is 10 to the minus 3. And we get about 1/2 times 0.1, or 0.05 meters per second. So simply by passing through that slit, the velocity of the electrons in the x direction becomes uncertain by 0.05 meters per second. And that's an issue because it takes the electrons some time to fall from the top to the bottom. Okay? So the distance they fall is, of course, 1/2 g times t squared. So t should be square root of 2g d over g, which is about 1 second. Okay? And that allows us to find the uncertainty in their position due to the uncertainty in the velocity. Okay? So this is approximately delta Vx times t. And so you can see this is 0.05 meters per second times 1 second, which is 0.05 meters, or 5 centimeters. Okay, so can you do it? Can you drop the electrons into the cup? You're probably going to miss. Now, I just wanted to illustrate how this works here. We found the initial uncertainty in position. We used that to find an uncertainty in their velocity, and then we used that to solve the rest of the problem. When we got done, we saw that the uncertainty in position due to velocity is much, much larger than the initial uncertainty in position. So we didn't have to use that troublesome general formula. This formula was plenty accurate for what we're doing, okay? And so we found our result. Anyway, I just wanted to show you that. It's kind of a cute problem. Okay, let's stop.